So tell me, let's ask the usual question. When did you get into CCS, Meihong?
And the year 2004, when I was working for Airstone Power in Leicester, we had a DTI funded project, which is look at power plants modeling and how to work with CCS. That's in the year 2004, 2005.
So was that with Doosan and
Doosan Babcock, and also Ardent Power, and also 3 companies.
So Fluor was doing the capture.
Yes, that one, right? And it's Ardent Power, Doosan Babcock, and Airstone Power, PSC Limited. These companies and one university. Yes.
And then
after that one, I moved to Cranfield in the year 2006.
Okay.
Yeah.
And Cranfield, what were you doing at Cranfield? What was the?
Oh yes, in Cranfield, my job was like a lecture in process system engineering. So we developed the interest for power plants and carbon capture, CCS. Mm-hmm. And I remember I joined the first meeting organized by you, which is November 2009 at Imperial College London. Do you remember?
Well, I remember it like it was yesterday, Meihong. No. Sorry, I think CCS meetings for me have gone into a bit of a blur, but
yes,
I wonder when that was. Gosh, that was a long time ago.
Yes, and in 2010, I joined as a partner for NERC funded CCS Whole System project. Mm-hmm. And in 2002, I remember you led a big Israel project called Gas Facts. I was one of the partners.
Yeah, that's right.
And in 2014, there was a competition by UKCCSRC for proposal successful, and I led one in carbon capture with intensified carbon capture using RPB, 1.27 million with Imperial and Sheffield, Professor Meihong Wang, and also Newcastle University. Yeah,
and that's still rotating, right?
Yeah, rotating. Yes.
Still going around. Yes.
yes.
Are you going to tell us any about
that? RPB has great potential, I think. Now, some companies have strong interest.
Yeah.
And I will talk a bit about this one.
Okay.
And then in 2016, I joined your UKCCSRC the application as a core member of core team. Yeah. Yep. Thanks. And recently, last year, I got a proposal for which is EU RISE project, which is like UK, myself, University Hull, and Dr. Annie Oku, and Belgium, and also Norway, in collaboration with China. We talk about carbon capture and utilization, CCUS for industry, which is ethylene industry, through system engineering techniques, like including AI and machine learning.
Okay.
Yeah.
You presume you're going to tell us a bit about that. And
yes.
Then, I mean, what's your sort of ambition in CCS, would you say?
I would say, as a professor, as an academic, we hope, first, we train people, the next generation people, and also we get insights for industry to implement. We can help industry to achieve their goal. And collaboration with industry is the most important factor in my life. I remember in 2004, 2005, when I joined the DTI funded project, then we had an industrial involvement. When I joined Cranfield, I asked for industry for some small money for PhD scholarship. We got a gentleman called Dr. Peter Stephenson from Ardent Power. He was very heavily involved in pay the money and supervision of PhD with me. And now you can see the graduates like Dr. Eddie Lavar. He's now very active in NIPA. And another of my PhD students, Dr. Annie Oku, he's a lecturer at Howard University. So we are glad to see we train people. We pass the skill and insights to industry. Maybe that's the most important factor. What do you think?
Yeah, no, I think so. I think it's very, very good.
Yes.
And I mean, the only thing I worry about a bit is that I don't think even now research councils really understand the importance of linking with industry. and doing. I mean, I think research councils are too willing to fund things that are new, just because they're new, rather than reflecting there's a lot of work you need to do so that you can conduct what you already do, but better.
Yes, I agree with you.
There's a big advantage in doing something better than doing something completely new and having to learn it all over again.
John, could I just say your statement, in my opinion, is totally correct if it's said for Great Britain. It's not true for the United States of America, and it's triply squared true for Australia.
What? Which one?
That the research councils and industry don't seem to understand that they could benefit from each other.
Yeah, well, I mean, I think there's an understanding and it's growing, but as I say, I think it's still the case that you know, doing things better is not, the power of that is not fully understood. Okay, very good. Well, I'll get off my soapbox and let Meihong actually do what he's here to do. Go ahead, Meihong.
Thank you. Yeah, please, so I will start to share. I will try to start to share the screen. Yes.
Okay, microphones off, please, people. And you can put questions in the chat.
And thanks everyone for coming. I will try my best to do a good job to let you feel a bit benefit from this talk. Okay. And the talk with the title is System Engineering for CCUS, Carbon Capture, Utilization, and Storage. And as introduced, my name is Meihong Wang. I'm based in Chemical and Biology Engineering at Sheffield. So today we will start with a very brief introduction. What's system engineering? Then we come to why do we do this research? And then we come to very brief introduction to CCUS. The main part is our research. Start from here. First one, modeling of PCC using solvents. First bit, we talk about dynamic modeling of PCC using MEA solvent for coal-fired power plant. Then we look at the second bit of first one modeling. We look at system modeling of PCC using RPB with MEA, again for coal-fired power plant. Then we look at the third bit, is first one modeling. We look at system modeling of PCC using new solvents, which is pipetting for gas-fired power plants. Okay, and then we look at first one modeling of CO2 transport through pipeline. Follow that one, we talk very briefly to the nonlinear system identification and the control of PCC using solvents. In the end, we have something very interesting, which is here, simultaneous carbon capture and utilization for ethylene plants. Okay, finally, conclusion will be drawn and the future research will be pointed out. Here we start section one, which is what system? Generally, we talk system is a set of things working together, okay, to achieve a function. One example is here, we have a wastewater treatment plant, and with wastewater coming in and treated water go out, achieve a function, okay. Now we go to what's system engineering, okay. System engineering is to guide different engineering as a bridge to make them work together. So in other words, system engineering is focused on the system as a whole, and it emphasizes its total operation. Now we come to what's process engineering. As we discussed, is a body of knowledge in system engineering, and then deal with like understanding and development of procedures, provide methods, tools, and people. In other words, we talk about training of the new generation of engineers and provide system engineering tools, modeling simulation or modulation, like even molecular simulation, and dealing with process design, operation, measurement, and control. Now we talk about system engineering, the key features. So first is interdisciplinary. We are very easy to think about chemical engineering, mechanical engineering, mathematicians, chemistry, and management. Also, we think about computing together. So it's like you use different knowledge to work together. And process engineering close part with development in computing, okay? Because today, the computer hardware, software, hardware fast enough, and software more complex, okay, to achieve the function we want to do. And the PSE can deal with multi-scale industrial or physical problems. For example, large scale we look at a refinery from purchasing of different crude oils to transport, to pipeline, and to the port, from the port to refinery, to different products and dispute that could be hugely complex. We could be as small as in the molecular level. We think about molecular modeling and simulation. There are also lots of applications in CCUS area. Now we look at motivation for this research. And one prediction by EIA 2016, it says predicted about 40% rise in world energy demand between 2020 and 2040. For energy research, we have a trilemma, which is first is energy security. We want to like turn on lights, then we have the electricity to use. And then we want to think about affordability, cost not too high. And then we look at carbon emissions. We cannot be dirty, and then net zero is a very important target to pursue. So therefore, any solution, you can't have an either solution solve any problem. You can only find something compromise in between. Now we look at CO2 emissions. Like CO2 is the main greenhouse gas. And then we have currently atmospheric CO2 level in the Earth is around 419 ppm. And it is increasing like 2 to 3 ppm annually. And then look at the potential of climate change, okay? And if business as usual, it will be disaster. The good thing is we have the Paris Climate Change Agreement, in December 2015, and hope to, temperature increase not more than 2 degrees or even below 1.5. In the UK, we have the new target require the government to bring the whole country to bring all greenhouse gas emissions to net zero by 2050, which is compared with the previous target, at least 80% reduction from 1990 levels. Now we look at our research generally, as we discussed. We look at process modeling simulation, optimization, and control, these kind of system engineering tools. And recently, we also have done some work in molecular simulation. And we look at application areas like power plants and carbon capture, CO2 transport, and utilization, and then grid-scale energy storage and bioenergy. Today, we were more focused on power plants and CCUS here. And then we finally, our work were used for process design, process operation, process control. And then we call our group is process and energy system engineering group. Generally, and at the peak time, we had 5 postdocs. That's from 2017 to 2019. Okay, and then now we have 3 postdocs, and then we have different PhD students. Now we have 15 up limit, and then we have also 1 visiting student from China. And so that's our picture of researchers and research areas and research methodologies. Now we come to the third part, a brief introduction to CCS, to pay the grant. This is a definition from IPCC. And then we have 3 stages: carbon capture, CO2 storage, and transportation. The capture stage costs a lot of energy and cost, okay? And then this one is a value chain for CCUS. We talk about where is the source, like power generation is a huge place. And we have natural gas processing, we have industry, refinery, and steel making. And then we have, when we capture CO2, how to transport. We either use ship like this, or we use pipeline like this. Where does CO2 go? And currently in North America, we have somewhere called enhanced oil recovery. And a majority of CO2 have to go to storage due to the huge amount captured, once captured. But we have something in between here, using new chemical process, using new catalyst, convert CO2 into chemicals or fuels. That could be another point to complement each other for the 3 destinations or sinks. Now we come to carbon capture approaches. We have post-combustion, pre-combustion, oxygen, and industry. And my work mainly focuses on post-combustion with some part in industry. So now we go to different CO2 separation approaches. We have using solvents, using solid, using cryogenic, using membrane, or others. I will mainly focus on absorption, especially the CO2 with solvents, with chemical reactions. We call it chemical absorption. We also have a bit of absorption, but we will not talk today. So now we go to the block flow diagram for standard CO2 capture based on chemical absorption. We have huge equipment such as absorber and stripper. We have other things like a condenser or boiler, and we also have cross heat exchanger. And these are for the pre-processing of flue gas before coming to the process. Okay, now we go to here. Anything we do system engineering, we must forget. We cannot forget. Everything come from practice. So therefore, we look at pilot plants, okay, to provide data, to provide insights, and then we can rely on. And in the year 2008 to 2009, when we start to collaborate with Ardent Power for the research in carbon capture, they had a facility 1 ton CO2 per day. In 2020, they changed direction. Then this facility now becomes UKCCSRC packed facility in the suburb of Sheffield. Then we have this one in the Texas at Austin. The pilot can capture around 3 tons CO2 per day, and which is very popular to generate lots of experimental data widely used worldwide. We have another successful example in Canada, which is Boundary Dam South Power, for around 4 tons CO2 per day. Okay, I reviewed these in early time in 2011. This paper is well started by over 1,000 times so far. And then we look at other facilities like Dong Energy in Denmark, 24 tons per day of CO2, and look at Ferry Bridge and something quite big, 100 tons CO2 per day, and around from 2013 or 2014, 15, something like that. Very short period, like 2 years. And we have another one very big, is in Norway, TCM, Technology Center Mongstad, and can capture around 200 tons CO2 per day. And then we look at commercial deployment of the technology, and in Canada, they have the Boundary Dam project, and which can capture 1 million tons CO2 per year, commissioned in 2014 October. And then the main point for me to mention is this is the first large-scale deployment of CCS technology into power plants, okay, coal-fired power plants. This one is the Quest project, again in Canada, which is run by Shell, and then capture 1.1 million tons CO2 per year, and then the world's first CCS integrated to part of refinery, which is oil sand upgrade. Now we look at our research. The first bit is first principle modeling of PCC using solvents, which we talk about what's the process we have introduced just now. Now we look at the complexity of levels of when we do modeling. We have different consideration regarding mass transfer and chemical reaction. So we have different models, look at rate-based models or equilibrium-based models. We also look at like our work in GPROMS model builder, which is a rate-based model and dynamic, developed based on two-film theory. I would say the GPROMS model builder is a very powerful platform to develop these kind of models. And we collaborate with PS Limited, Professor Costas, and then we developed something from 2007 to 2010, 11, a series of research. Okay, and here we would say this is the flow sheet, and it looks like in the GPROMS, okay, and like absorber model and a stripper model in dynamics. Whenever we do model, we want to validate to see whether the model makes sense. And currently, my personal observation is look at different publications. The model generally like validate very simply from 1 or 2 aspects, not robustly. Now, for this model, we did the different research, and we used Dugas 2006, the data from experimental data from Texas. And then we have like choose very different cases, okay, and look at different CO2 capture levels. And then we also found some data dynamically transition from one case to another. And then we carry out the validation, and we found quite satisfactory for the temperature profile and rich loading and compare with experimental data. And in addition to the statistical model validation, we also look at the dynamic model validation. And again, lots of paper generally didn't bother to think about dynamically how to validate things. And we did this one quite early in 2011 and published in 2012. And for this is the whole flow sheet in GPROM model build. And then we select from the data provided by Ardent Power with the facility at a DITCOT at that time. And then we look at what's model predictions compare with the lab measurements. And then we look at this one, and then we have look at temperature profiles over a period of 8 to 9 hours. We are glad to say the trend can change very, very good. And we also look at the reported duty, which also changed very clearly, and the trend is very good. We look at the CO2 concentration in the treated gas. We found it changes, it's consistent, but with a small gap. And we try to find why. There are two reasons in our mind. One is we assume chemical equilibrium happened between MEA, the solvent, and CO2 reaction. Actually, it takes a bit of time. Even though the reaction is fast, it could be, very ideal. Another reason could be on our weighted area. That could be estimate a bit higher of the contact area, things like that. But we are not 100% sure. We just predicted what would happen. And here I provide more details. So if you have interest, you can look at these papers. And then when we have a model, we have validated, how can we use the model, okay, for process analysis? In the year 2009, 2010, 2011, we have done lots of analysis using the validated model. For example, in one case, we look at when we have flue gas ramp down because of the power generation requirement. Then if we keep the lean MEA, the lean solvent, flow rate the same, then how would it happen in the operation of such a absorber using packed column? The dynamics after 100 seconds, 300 seconds, 400 seconds, until 1000 seconds, which is something here. So therefore, we can see how things change. Why in this curve? Because of the increased LG ratio. Then we look at if we change another scenario, if we make the lean solvent change in the ratio. In other words, we keep LG ratio nearly the same for this case. We can see the operation of the absorber would be more stable. This work, and we published in this one, is highly cited in Web Science. Okay, and this is just an example. Actually, we also analyzed the water balance. We also analyzed other scenarios like dynamics. Okay, now we move to scale up. Because the company, Ardent Power, when they funded the project, they asked us a question: what would happen if we use solvent-based carbon capture for 500 subcritical coal-fired power plant? That's a question raised in the year 2007, and we answered in 2010, 2011. Okay, and this one is for the scale up, and then we look at different decision making, like if we choose different columns and the size, what could be. So in the end, we also calculate like a mass transfer coefficient, mass transfer flux, and the surface area of packing required. And we also look at the packing volume required. Okay, now we can say for 500 subcritical coal-fired power plant, when we have 600 kg per second of the flue gas, and if we want to capture 90% of the CO2, then we need 4 columns, okay, for absorber, 2 columns for stripper, at a very big size of 12 meters roughly in diameter. and we use 30% of weight percentage of MEA, and then assume the lean loading at 0.29. And then we look at how to integrate through the modular side. We look at the flue gas from power plant, and then pre-process and come into inlet of the absorber. And then we look at how to take steam from a power plant into the carbon capture plant. And then we look at integrated system, which is this is a power plant. This is a carbon capture plant. Then we look at the static performance and dynamic performance. And then we can see if such a plant, originally has the thermal efficiency around 37%, then could drop to 27%. Okay, and then the reason why, because we take steam out from LP and IP LP crossover, and that flow rate originally was 348 kg per second, now dropped to 160 kg per second. Okay, and then dynamically, if there is a core from national grid, this power plant has to drop its output from 442 to like a 418. Okay, and then the flue gas, obviously we have to reduce the core burning rate. Therefore, the CO2 flue gas flow rate will reduce. The steam from the power plant for carbon capture regeneration solvent will reduce. Then dynamically, we can see, here the different variables. How do they work together? We can see here use hours as the time limit. If we use minutes, we'll see it's a very slow process to achieve the new steady state. Therefore, we can say clearly it's a fast power plant with a very slow carbon capture plant. Okay, this work was funded by Artificial Power from 2007 to 2010. And then we also have the NERC project funded by National Environment Research Council, okay, in collaboration with Imperial College London, University of Sussex, and British Geological Survey, okay, from 2010 to 2014. Okay, so now we move to the second bit of first principle modeling of PCC. And we look at why do we need process intensification? Okay, as we mentioned from Lawar et al. 2012, study of 500 megawatt of the separate group power plant, we can see we have 600 kg per second of flue gas, which is huge per second. Okay, then we capture over 8,000 tons of CO2 per day. Then we can say the size of the pack column as absorber and strippers are huge in size. This transfer into the very high capital cost. And then we move to key findings from Billiok et al. 2012. We look at the process, which is mass transfer limited, okay, because MEA with CO2 the reaction very fast. And then we look at why it's mass transfer limited, because of the flow pattern inside the vacuum. Then we look at the dynamics, again, from Lawar et al. Then we look at here is dynamics is very slow. Why slow? Because very high energy ratio to achieve 90% CO2 capture, which is roughly 5.5 to 1 or 6 to 1. In other words, for 600 kg per second of flue gas, you need roughly 3 tons of lean solvents in circulation per second. And you need to regenerate the solvents. So that's why the energy consumption is huge. As we said, very slow dynamics would be the operation challenges for when the carbon capture plant is linked to integrate to the power plant. So again, we look at intensification. Process intensification is a strategy for making the major reduction in the volume of processing plant without compromising its capability. So PI also refers to reduction of number of units, okay, by combining 2 or more unit operations into one, resulting in reduced capital and operating costs. And RPB, rotated backbed, is one of the PI technologies proposed by Professor Remshaw in 1979. That's worldwide the first person to talk about the process intensive technology. And I was lucky to meet Professor Remshaw from 2006 to to 2012 when I was at Cranfield University, because Colin was visiting professor at Cranfield University. And then RPP takes advantage of centrifugal forces to generate high gravity and consequently boost the mass transfer performance. Right-hand side, you can see we have a huge column, okay? And this is used pack column. And this one, how small it could be using the RPP. And this figure was from Dow Chemicals, okay, for their reactive separation. Now we look at the grant we have done, in 2014, and we won a big grant, 1.27 million. I was the PI for the whole consortium in collaboration with Imperial College London and University of Sheffield and Newcastle University. And we, over 4.5 years, we look at how to use RPP technology for process intensification in carbon capture. Okay, and for this work, we look at design of the new equipment. For RPP absorber, it's straightforward. For RPP stripper, it will be very challenging. Why? Because if you do RPP body for stripper, if you have a huge reboiler, that would looks very awkward. So therefore, how to put these two together using spinning disk technology, using steam outside, and then provide the source to here to the RPP body. And this was the design, and in collaboration with Professor Colin Ramshaw and Dr. John Lee, and we achieved the design. And then we have with the new equipment here, as we mentioned, and then RPP absorber. Then we look at how to recover the energy from the system. Then we propose a new block process flow diagram. This is put in this review paper in 2015. Okay. Now we look at here. Once we have equipment, once we have a new process, how can we assess the effect of RPP technology for intensified carbon capture? Here we use Osmo Plus very quickly, write fortune routing, dynamic link together, run the simulation, do the modulation, and with experimental data from Newcastle, which is Justin et al. 2007, and from Taiwan, Chen et al. 2013. Then we look at how the size of the equipment can be reduced. We have the conclusion here, preliminary. The packing volume in the absorber can reduce 52 times. And the absorber column size could be reduced like 12 times. And then for the stripper, we say the packing volume can reduce like 30 times, and the stripper size can reduce 8 times. Then with 32.9% of the MEA, we found the energy consumption is similar. Why similar? Because originally the reboiler duty would be lower, but now because of rotating, we have to provide energy for rotating. Okay, so that's why we say it's comparable. However, looking at the future, with RPP technology, we can use higher concentration of the MEA, like 55%, 65%, or even 75%. Now we are working very hard to determine an optimal point, which is not easy. Yeah, and then we can quantify the performance of the new values for these above. Okay, and if you have interest, we have these papers published recently, and you're welcome to check these papers. Now we move to first principle modeling, the part 3. We look at with packed column, but new solvents. Because if you notice that my previous 2 sections, we look at MEA only, because MEA is a standard solvent used in our evaluation of different technologies. Now we look at new solvents, piperazine. Why do we turn our eyes into piperazine? Because it reacts with CO2 solvent, reacts with so fast. Higher CO2 absorption capacity, slightly lower regeneration energy, and then also more stable if we talk about thermal and under oxygen environment. And then we look at 30 to 40% weight percent of piperazine. And these are the details. How did we develop models? Okay, and these are the details how did we validate the models using data from Texas, okay, and Austin, and Plaza and Roche published in 2011. They did share lots of data, which is a very big advantage for our modeling researchers. And then we look at model validation. We are very confident the model makes sense because area is quite small. Okay, and then we look at how to do scale up of different configurations into the commercial size for 250 megawatt NGCC power plant, or we sometimes call CCGT power plant. We mean natural gas fired combined cycle power plant. Okay, here is the size. Here is our context. We think about two different solvents, which is MES at 30% and PPAZ at 30%, 35%, or 40%. Okay, we look at three different scenarios. One is standard configuration. One is absorber intercooling, like here, absorber intercooling. One is absorber intercooling, like here, plus advanced flash strip AFS. So now we look at 30% PZ versus 30% of MEA. Now we look at how do we define the energy consumption as we discussed, because now we will have more details regarding evaluation of PPAZ at a large scale. Standard process, you can look at different kind of concentration of MEA, 30%, and then 30, 35, and 40% of PZ. Okay, the energy consumption here. And then intercooling, we have this table, and then look at for PPAZ and for intercooling and AFS. Okay, we got a conclusion because in our group, we participated in 2013, very early times. Look at a pack column. If we use pack column, use MEA at 30%, the energy consumption could be as high as 5.34 gigajoule per ton of CO2. And now if we use PPAZ at 40%, and then we use intercooling and AFS, we can achieve as low as 2.76 gigajoule per ton of CO2. Okay, and now we can say the latter is 47% lower. In other words, it's nearly half. Okay, compared with 30% MEA with standard configuration. Now we look at economic index. Okay, we look at here. The conclusion is originally, if we use 30% MEA, use standard configuration, the cost could be like $61 per ton CO2 captured. Now using PPAZ at 40% and using intercooling and AFS, and we can say we can achieve a reduction to $34.65 per ton of CO2. This is 42% lower, again, close to half compared with 30% of MEA. So therefore, we can confidently say 40% weight percentage of PPAZ solvent brings practical benefits, technically and economically, for large-scale application to PCC. This paper was very recently published in Applied Energy. This figure demonstrates what we want to say. Two different solvents, three different configurations, and how to reduce energy consumption. Now we look at here, we move to first modeling for CO2 transport. This figure is the very commonly used pure CO2, the phase diagram. Like this is supercritical CO2, this is dense phase CO2, and this is vapor, this is liquid, and then we have to operate in this region for CO2 transport. Okay, we from 2012 to 2016, I was based at Harvard University. So then we look at in Humber region, the UK's largest CO2 emission area. And then we look at the large scale emitters. We mean over 1 million tons CO2 per year, the emitters. We found 12, like a Drax power plant and Ferry Bridge and Hatfield and Salt End, and these kind of names industrial people will be very happy to hear. They are at different locations with different amounts. How to design the CO2 transport pipeline in the long term achieve the benefit. So we look at the solutions, option 1 and option 2. Okay, the option 1 is if we assume use one pipeline. We have scenario 1, which is a fixed pipeline diameter. Another one is use varied pipeline diameter. Another one we use 2 different pipelines at 10 years apart. In other words, we have phase 1 in the blue line. We have red line for phase 2. And then phase 2 will be 10 years after phase 1. Okay. And then we look at this one, we can say option 1, scenario 2, consistently show better economic performance. The work was done in 2011, 2012, improved in 2013, and published in 2014. And we spent lots of time, talk to industry, talk to people, and then improve the quality. In the end, we attract IMAC Ludwig Bond Prize in 2014 to recognize our contribution to the process industry. Now we look at a recent study, which is nonlinear, because previously the 4 sections we talked about first principle modeling. And now we look at data-driven modeling, which is system identification and control. Here is an example. We have done nonlinear analysis for carbon capture plant to show how nonlinear it will be. The higher the capture level, the higher the nonlinearity. And then we do linear system identification at different local points. And then we piece together. The whole model is nonlinear, but in the region, it will be linear. Okay. Then we look at another study, which is choose NACS model, nonlinear NACS model. And then we use a forward regression with orthogonal least square algorithm to determine the model order and the parameters. And then we compare the benefits of nonlinear model with linear model to show the advantages of the methods. If you have interest, you can look at details here. Now we move to, we use nonlinear MPC, model process control, to control the process, okay? And then we can see how does it implement it. And then we look at different cases. What's the benefits? Look at here, the integral squared area. And the benefits is that ISE would be much lower for our nonlinear MPC. Now we move to a very recent study, which is simultaneous carbon capture and CO2 utilization for ethylene plant industry. Global ethylene demand is around 170 million tons per year now, and manufacturing 1 ton of ethylene generally produce 1 ton to 2 tons of CO2, depending on which feedstock we will use, either naphtha or propane. And then thermal cracking furnace is the heart of any ethylene plant. You look at here is one of the thermal cracking furnace. And then we look at if you have an industrial plant, ethylene plant, and if you, for this plant far away, and you do carbon capture CCS, you would think about CO2 transport and storage, okay? However, if there is a small plant, you do simultaneous carbon capture and then convert CO2 into chemicals or fuels. That would be also be very attractive. So that's why in collaboration with 2 different research groups in Shanghai, and we developed this new research, very, very novel. Design and lab synthesis of new dual function materials. Why do we mean say dual function? We mean as adsorbent and also as catalyst. And the new process, we integrate the calcium looping and reverse water gas shift reaction. And then we implement in one fixed bed reactor operating at 650 degrees. And then step 1, carbon capture using adsorbents for flue gases. Step 2, switch to excess hydrogen, and then under iron and cobalt catalyst, in situ conversion into CO, and then syngas, which mixture of hydrogen and CO is the product, and then which can be further used for Fischer-Tropsch synthesis. The research was done through experimental study, molecular simulation, modeling and simulation, and for scale up. and also technical economic analysis. So this is the lab experiment using 10% of CO2, 90% of nitrogen as simulated flue gas for carbon capture. And then to explore stability of the material, DFM. And then we look at here, do 10 cycles. From this figure, you can see over the 10 cycles and the CO2 capture capacity is always around 9 mole per kg of solvent. And then the CO2 conversion is always around 90%, up to 90%. And then here you can see CO2 selectivity is also close to 100%. And then we look at scale-up study. And then initially, the work was done using 0.25 G of the material. And then in a very small fixed bed reactor. Then we use 100 times bigger, 25 G. And using a much bigger fixed bed reactor, we look at 2,000 milliliter per minute of the flue gas. Above this limit, we can no longer use lab facility to do experiments due to safety concerns, because hydrogen is easy to be exploded. And then we use modeling and simulation to help scale up into commercial scale for 100,000 tons per year of ethylene plant. Now we need a huge packed bed, 2.5 meters in diameter and 5 and then how many meters in length. And then we need 50 tons of the material. The flue gas around 23 kg per second. And then we capture 11.87 tons of CO2 per hour. And then we look at technical economic analysis, which is for this large scale ethylene plant, assume 8,000 hours per year, which is common sense for a plant. And then we look at the cost is around $165 per ton of CO2. This is in comparison with individual steps. If we do RWGS and CAR, that could be $393 per ton of CO2. That means the new process, the cost is only like 42% of 2 separate steps. So this paper was very recently published in Energy Environment Science with SI impact factor over 30. Okay, if you have interest, you are welcome to look at the details. And now it's time to draw a conclusion for what I have talked, mainly through first-order modeling to data-driven modeling, using modeling as a tool to predict the performance. And of course, we must always say we must work with people do experiments through power plants. We must also talk to industrial people to get insights. Okay, and we also look at process intensification. It has great potential to reduce the costs and for carbon capture, and more importantly, for footprint of carbon capture plant. And then for CO2 transport, preliminary design for pipelines for the Humber region. And then simultaneously, carbon capture and utilization could be attractive for some cases. For example, if you have a small plant in an isolated place. Now we look at the impact of our research, and our model has been used by Urban Power because they fund our research, and then for their internal R&D. And then for PS Limited, when they develop GCCS, they use part of our detailed carbon capture model, very detailed, as part of their GCCS, simplified model. And then we also have different awards like a Ludwig Monod Prize and a Sage Baseball Prize. And then we, in 2019, and Nigerian Prize for Science invited me and my former postdoc to be the joint winners. And these are the highly cited paper in this area. And in this case, here you can see different papers, review paper or research paper attract lots of citations worldwide. And then we talk about LASIK et al. 2013. Very recently, and in the year 2020, our UK government, Department of Business, Energy and Industrial Strategy, had a report for CO2 development at the disturbance industrial sites. They select like around 10 cases from worldwide. They put our case in the appendix with details. And my former PhD student, former postdoc, now lecturer at Harvard University, Dr. Enioku, was very excited to remind me, and we have something attract attention. And then look at the future. I always think about different tools, from process modeling, simulation, optimization, to molecular simulation, and then to large-scale simulation and optimization. And then we look at future directions. We are working for carbon capture, for power plants, and for industrial processes. BECCS, and recently a group of researchers, including Professor John Gibbs and myself, we put a proposal in BECCS, and also direct air capture, and also CO2 utilization. That's why we have 15 PhD students put in very different areas. And very recently, like earlier this year, we do big data and artificial intelligence for modeling, simulation, and optimization control of CCS process. And then this is a new grant from EU, European Commission, and a RISE scheme, Research and Innovation Staff Exchange, from August 2021 to 2025. We should have started from January 2021, but because of the pandemic, we couldn't start. We use a fancy name called Optimal. So that's very easy for anybody to remember. Our work is smart and CO2 neutral on-film production based through artificial intelligence and machine learning. And these are the work programs. In the end, I want to say thank you for all the sponsors, start from UK Research Council, UKCCSRC, NERC, and EU FP7 and Horizon 2020. And also industry like Ardent Power pay me the first money in the year 2007, which is not easy. And the BF2I paid me something in 2009, 2010, and then Aerosol Power 2013, and the Carbon Clean also very closely work with me and with lots of support. And then also thank to industrial collaborators, and not only Aerosol Power, Carbon Clean, Costain, Uliper, National Grid, PSC Limited, and Ardent Power. And also thank to my past and current research staff and PhD students for their hard work. In the end, I want to thank our friends in UKCCSRC. This is a great platform for us to work together, and thank you for your time. Thank you very much.
Okay, thank you, Meihong. Well, we don't have very much time left, so we better move quickly to questions if you don't mind. So there's a couple of questions in the chat. Bart de Groot, are you still there? Could you want to come on and ask your question? It's quite a complicated question.
Okay, yeah.
Are you there, Bart?
I don't see him still on the participant list.
Okay, thank you. Okay, in that case then, we've got a question from Ina Kim at Sintef about the rotating packed bed.
Sorry. In this screen, Caris, I couldn't see the talk.
Oh. Okay, on the chat. I'll ask you anyway.
Oh, you chat now. Yes, better. Yes, thank you.
So, question about the status of the rotating packed bed, Meihong.
Sorry.
Status, and also questions about corrosion issues with high concentrations of MEA.
Oh yes, that's a good problem. When we did the work, started to discuss higher concentration of MEA would have higher corrosion rate. Yes, and then the solution could be used coating, because Professor Remshaw and remind us use coating and in the surface of the material. That could be a solution, but I'm not an expert in corrosion. I believe in CBE at Sheffield, we have a young colleague, Dr. Kara Campbell. She's a big expert in this area.
Okay. And another question from Ashrafi, if you want to. Oh, Ina's there. Good. Did you want to follow up on that, Ina? Did you have any comments?
I just wanted to ask, what is the status? Are you continuing to work with this rotating pack bag? And you probably heard about Norwegian company 3C also having this technology.
Yes, I guess you mean in Norway, part of Sintef, right? And yes. We have Professor Dek Aime and Dr. Jiru Ying. Yes, we are in close contact. Yes, but slightly different in technologies. Like say, RPP absorber could be the same. RPP stripper could be slightly different. Okay, and also for modeling side. And here in the UK, we have lots of work. Start from like process modeling and to Professor Mohammed Pukshanil's team in CFD study and to Imperial College London and lots of study. Okay, and then that's RPP study. Yes, we know each other and we work together in the new EU funded project. Yes.
Thank you.
Okay, and the question from, I don't know how to pronounce it, Rafi on the solvent selection.
Oh, yes. I guess this question means like when we talk about first part of first modeling, we use MEA. And the second one for RPP, we still use MEA. But for the third part, we look at PZ. Why? Because we think for carbon capture, if we want to reduce cost and also reduce energy consumption, we have to think about new solvents and new process. Because RPP is new process. The absorber intercooler is also new process. And also we look at advanced fast stripper, which is also ASF, is also has also a kind of new process. Yes.
Okay. Any more questions, anyone?
Yes, John, I saw a question from PS Limited. But the root.
Yes, yes, early.
Thank you for the question for cost. I'll say, can you expand a bit on what you mean? What is a separation stage? Oh, yes. Separation stage, we mean separation of flue, like CO2 from flue gas, which is carbon capture. And then when we talk about the cost, it's a very generic talk. You know, individual case, the percentage will be very different. Okay. And then we talk about, because as you point out, we have capital cost, we have operating cost, we have total cost. Yes, when we talk about cost, we mean both. We mean all put together, okay? And we also mean like 30 years, the capital cost should be spread, okay? Yeah. Is that good?
I think so. I was going to ask him if he could ask the question himself, but he's not there. So that sounded pretty comprehensive anyway.
Yeah.
Okay, well, I think we've reached the time. If we don't have any more questions, I'll just ask one more, I think, Meihong. On stopping and on sort of flexibility and stopping and starting, what do you think the future is going to be for power plants with capture? Do you think they're going to be able to be base load, or do you think they'll have to be quite flexible?
I think if we use RPP technology, it's very fast.
But you think
for conventional packed bed column, unless we have very good solvents, otherwise we have to think about flexibility study a lot and do lots of research. Because we have a study, because in the year from 2012 from 2011, I remember, to 2015, funded by BF2RA, we had a PhD research. Think about the UK use power plants, how to add carbon capture, then certify the UK grid code. In the UK, we are a small grid compared with China, USA, or European continent. Our grid code is very tight. In other words, you have to operate very, very quickly. And then previously we had a supercritical power plant. We have a huge drum in the power plants. That could be good for us. But now if we use new technology like a supercritical power plant for better efficiency, that could be very challenging to operate. And we put several proposals how to make it more flexible. Yes, I agree with your question and the comments, John, is the flexibility for power plant use capture could be a problem. Yes.
Okay. Yeah. I mean, there's a just for the audience. There's a study done for Bayes as well on flexibility of post-combustion power plants on gas turbines. Recently, they're obviously concerned about it, but it came up with some ideas. Anyway, okay, Meihong, thank you very much. Thanks for a very comprehensive presentation. For those that couldn't follow the slides fast enough, they will be up on the website, so you can look at it. And I've no doubt, Meihong, you'll take any questions, follow-on questions by email later if people want to follow up some of the details. Would you be able to do that for us?
Yes, John, thanks for your invitation. This is a very good platform to present in UKCCSRC. Yes, if you have any question, please email me. And for the presentation, I will send a PDF version to Caris, and she will put in the website so you can download.
Right, and the presentation will be recorded as well. Okay, Caris, any last words?
No, well, I've got a quick update of what we've got coming up next week. But first of all, I want to say thank you very much. Thank you very much for your talk today, Meihong. It was really interesting and really in depth as well. So there was a lot covered, which is great. And yeah, we look forward to having the video and the presentation on our website as well. So just to let everyone know, next week we've got one of our cluster updates coming up. So we've got Matthew Rose from the Black Country Cluster and Energy Capital speaking to us, and he'll be speaking on CCS from the perspective of an inland industrial cluster. What's in it for us? So it'll be interesting to hear from Matthew next week. So thank you everyone for attending today. Thank you for all of your questions, and thank you especially to Meihong for a great presentation for us. Thank you. Have a nice weekend, and hope everyone has some lovely weather as well to enjoy.
Bye.
Bye.